All right, can you all hear me okay? Okay. Let me make brighter in here. I want to talk about today really, and actually this week and next week, I want to talk about the next lab. And it's going to be our first written lab. So there's actually a lot of things I want to say because it'll be the first lab for which you're actually writing a report to me. And so I'm going to use some time this week and some time next week to discuss the lab. But I just want to say enough to get you started. I know you have the multimeter quiz to do. Get that done. At least this is recorded so you can go back and see what I said. There's one thing that I need to show you today is how to use graphing software, just in case you don't have graphical analysis. So this first written lab, which is our third lab, is called Ohm's Law and Electrical Resistance. And what you're going to do in this experiment is really test out Ohm's Law. The goal really is to learn how to wire a circuit. This is going to be a written lab report, but you're not really going to do a lot of error analysis like you've probably done in Physics 205. However, the next lab, you will do a ton of error analysis. Okay, but this one's really more focusing on really learning, getting familiar with wiring circuits. Yeah, you know what? Let me fix that real quick because I had the same issue yesterday with my other class. So the problem was I forgot to publish it. So let me go to the class real quick and I'll publish it because otherwise I'll forget. It should be there now. Okay. So question, is the quiz and the video assignment two different assignments? So regarding the multimeter video, I know there's a document associated with the video that requires you to fill out some information. If you show the filled out information in the video, you don't have to turn in the document. If you don't show the filled out information in the video, then you must turn in the video and the document. Does that make sense? For the multimeter quiz. Okay. So let's go back to the lab. Let me blow this up some more. So you have some equipment that's associated with this lab. There's two multimeters that you're going to be using. You have the, I'll say the cheaper multimeter and the better multimeter. I will say, when I created the lab over the summer, I actually used a different multimeter, which was better than your good one. The problem was that we weren't able to get it in time for this class. So, in fact, there's one part of the lab we can't do because of that. So we'll see how this one works out. The one I had really, was really awesome. It's just that we weren't able to get it in time. And it was also the right price too. So I need your feedback as to how the experiment goes. So you're going to require some equipment. Let me show you the equipment that you're going to be using for this lab. you're going to be needing a breadboard. Now, again, my breadboard is different than yours. This is the breadboard. This is the board on which you're going to build the circuits. Okay, so you're going to need this breadboard. You're going to need a power supply. And our power supply, now remember, we're trying to minimize cost. So our power supply is probably not what you would normally expect a power supply to look like. So let me grab it. Power supply looks just like a power adapter. This is your power supply. Notice the red switch on it. Okay, this is your actual power supply for the lab. The red switch has 6 settings that go from 3 to 12 volts. So you're only going to be able to get 6 data points for each part of the lab. Well, for parts 2 and 3. For parts 2 and 3, you're only going to be able to get 6 data points because you can only vary this 6 times, okay, between 3 and 12 volts. So it's going to be kind of a pain because you have to make your measurements with this, unplug it, change the switch, plug it back in, and then make another measurement. Unplug it, flip the switch. So it's a little bit more time consuming in that sense because you have to keep on unplugging this to be able to change the switch. So you're going to need a screwdriver. So you have this piece of equipment. You have the protoboard. Then you need a resistor. It's a 1000 ohm resistor, like this guy. And a diode. Now my diode probably looks different from yours. So all these came with your kit. There's also a card that comes with it that you need to know how to use. Now I don't have the card with me because it wasn't provided to me because my kit was older. There's a card which tells you how to decode the value of the resistance of a resistor. So if you actually pick up the resistors from your lab kit, you'll actually see a bunch of bands on the resistor. And the bands are different colors. And it's a color code that tells you what the resistance of the resistor should be. So I'll talk about that in a little bit. Okay, so there's not a lot of equipment that you're going to need to use beside the multimeters, and also you're also provided a light bulb. Because the power supply only goes to 12 volts, we can't do an experiment with the light bulb. So I actually had Tyler get landscaping bulb. These run at 12 volts. And so you're going to actually measure voltage as a function of current. Actually, you're going to be plotting voltage as a function of current, but you're going to be changing the voltage and measuring the current. Okay. So you're going to need that too. So that should all be in your kit. The light bulbs the little light bulbs that you use were really only for the multimeter quiz. Okay. Oh yeah, the last item too is and mine looks different from yours, is a potentiometer, which is a 3-terminal device with a dial on it. And that's just a resistor in which you can vary the value of the resistance depending on how you connect it. And I'll talk about this later too. So all these should be in your kit. So the first part of the lab, what you're going to do is you first got to know how to use the protoboard. So there's a picture of the protoboard. It's not exactly, hold on a second. It's not exactly the same as the protoboard that you got. In fact, the protoboard I showed you is very rectangular. The protoboard that you were given is more of a square shape. Okay. So I'm sorry, I missed the two questions. So Patrick, you had a question. If you have your own variable power supply, can you use it? Yeah, I get. Yeah, you probably get better data, because the power supply I'm giving you is not very well regulated. Once you start getting too much current, it acts funky. If you want to, Patrick, you have your own power supply. Go ahead and use it. But and Justin, should you measure the actual resistance? Yes. So in the lab, it's going to ask you. Let me scroll ahead. What the measured resistance is and what the color code resistance is, so you can compare. So yeah, you're going to need to measure that resistance with your multimeter. Okay. All right. So let's go back to this first part, because you need to figure out how this thing is wired. Basically, the protoboard is just a board with a bunch of holes in it, and you can just stick in the resistor or whatever electrical components you want to put in your circuit. The inside part of the protoboard, which you can't see, hold on, let me change view. Inside this protoboard are conductors, such that they connect electrically the holes together in a particular pattern. What you need to do is to figure out how the holes are electrically connected together. How do you do that? How do you figure out if the holes are electrically connected together? Well, what you do is you use the multimeter. Let me grab my multimeter. A second here. You grab the multimeter and you measure resistance. That's really all you have to do. And in fact, on this multimeter, the good one, there's a setting, and I have it set to that value right now, that allows you, or that setting, that allows you to actually measure continuity. Really, it's measuring resistance. You can measure the continuity or you can measure the resistance. If the resistance is very low, then you know that two items are connected together. So for example, if I measure the resistance between these two wires, oops, the meter gives me nothing. But if I choose a different pair of holes, can you hear the beeping? Okay, so it's beeping. That tells you that you have continuity. So it shows, I'll give an example. The two holes that you see there are connected together. You see the wire, how I wired it? Those two holes are connected together because the resistance is 0 or close to 0. I can set it to a resistance reading, and it says it's 0.14 ohms. Okay? So what you have to do, and you don't have to do every single pair of holes in this board, right? You have to go between two holes, let's say between pairs of holes, not every single pair, and see if they're connected together by measuring the resistance. And you'll see a pattern fairly quickly. And that'll tell you how the inside of this is connected together. That allows you to figure out how to wire a circuit. Okay. And what you'll do in the lab, you'll use a drawing tool probably. You'll use a drawing tool to tell me how these are wired together. So for example, if you know, I can use the line insert shape. Oops, sorry. Okay, in Word I can go to insert shape line. You know, I can draw a line like this, for example. Let me make the line thicker. That line's, let me make that line thicker. Okay, so there's, I made it too thick, but that gives you an idea of how I can draw lines in Word to show how they're connected. Okay, and again, you don't have to draw every single one out, just enough so that the reader can understand that you know what you're doing. Basically, you need to communicate to me that you know how this thing is wired. Okay? Does that all make sense? Okay. Now, that's part one, and you can't do part two until you understand how that board is wired. Now, if you look in the figure, there's these 4 terminals at the top. That's for a different protoboard that we usually provide when the class is on ground. Just ignore that. Okay, those are terminals that you can use to connect your power supply to. And you don't have that. Like I said, these are cheaper protoboards. Okay, sorry about that. Okay, we're trying to limit the cost. Even by limiting the cost, your kit costs over $250. All right, so in part 2, that's where we're going to look at Ohm's law. Now, in part 2, you're going to be required to create a graph. Does everybody have graphical analysis? I hope, if not, I have an alternative for you. Okay, so let me show you the alternative. Before I go on and talk about the rest of the lab, let me show you the alternative to graphical analysis. Okay? Yeah, the program. Okay, yeah. One of the issues with graphical analysis is if you update Windows or the Mac, in my case it was the Mac, one day about 15 minutes before class, I upgraded the operating system on my Mac because it asked me to update it, and went to class, and I couldn't use graphical analysis anymore. So I had to use a different program. And so the other program is called Cy Davis. So just in case, I'm going to show you where they get this program. It's actually more powerful than graphical analysis, and it's free. So in order to find it, and there's a document on Canvas, and I'll show you the document in a second. If you type Cy Davis, if you just do a search, I can spell, you'll get to this. This will be the first thing that shows up eventually, essentially. And I'm going to go to Cy Davis download. So you're able to get a newer version of graphical analysis for free? Patrick? Wow, because I thought it wasn't free. Okay. Anyway, if you can do that, that's fine. But I'm going to show you this one anyway because it's a little more. I think it's more powerful than graphical analysis. Oh, okay. Okay, that's good then. So they didn't change the code or anything. That's good. But anyway, let me just kind of show you this one. There's a download page. So the problem with the downloads, if you click this one, you might not get the version you want. So you go to Files. And here, if you hit download here, it's going to give you the source code. And unless you, and I think the source code, that source code is really for a Linux machine. And you have to know how to install it. So if you know how to use Linux, Ubuntu, or whatever, go ahead and use that version. But most people use PC or Mac, and so what you have to do is go to Cy Davis Beta right here and click on it, and then you have the list of software you need. The first one that you see is for the Mac, the DMG one. The second one, .msi, is for the Windows machine. Okay, so you can use either one of these two. So when you download it and install it, you get something that looks like, hold on a second. I'll open up a new project. Something that looks like this. So this is Cy Davis, I'm sorry. There's actually a program called SciMath too, and let me just show you how to plot data, enter data and plot data. So I'm going to enter some numbers. And there's an instruction document that I put in on Canvas. So I'm typing in numbers, and then let me just do this. I'm actually going to mess up one of these data points. Okay, so there's data right there that and I know it might be hard to see the numbers. I apologize. Okay, so I plotted the data. So if I want to plot a graph, all I got to do is click on the Y column and go to Plot, Scatter, and it gives me the graph right away. And then I can do curve fits, etc. So in order to, the next thing I need to do is put titles on this graph. So the x-axis, let's pretend is time. And of course you got to put units. You can change the font and the color and all that fun stuff if you want. And I'll put distance. This is what you would be doing in Physics 205, but and then the title, double click on the title and put distance. Notice how I'm putting units everywhere. And if you want, we can make that blue. So there's my graph with titles on it. So that's, I want to see titles on the graph just like you did in Physics 205. Mine was set up, mine is right now set up so that it puts a scale on the right hand side because of a project I'm working on. If you install yours, you won't see the scale on the right hand side of the graph. What did I create? So I went to graph. Hold on a second. I click on the table and I go plot and then scatter. Okay. And Justin is Cy Davis. Okay, let me go back to the graph. So the one thing that it doesn't do, the graphical analysis does, is when you do the curve fit, graphical analysis shows you right, it puts directly on the graph the curve fit results. This software does not do that. So that's going to be an extra step. So I'm going to do a curve fit to this. Yeah, mine did too. I mean, let me go back, Patrick. So if I go to this, and I hit plot, right? I said plot and then scatter. It's when I see the graph that the graph menu comes up. Okay. So let me do a curve fit to this. So I would go to analysis and first look under quick fit, because if you look under quick fit, you can do a linear fit right away. You always do a linear, when you do a linear fit, you do something, you do a fit with a Y, with a fitting parameter for the Y-intercept, okay? So I'm gonna do a linear fit and it does it right away. And there should be another window that pops up, which is on my other screen. Here it is. With the curve fitting parameters. And granted, they're kind of small, but I can see the curve fitting parameters. So what I would do is, then in my graph, I would go graph, add text on active layer. So I click here, and then I look at my graph, my slope, 1.0, and I'll fix that later. Is that one of these is a plus or minus symbol? I forget which one. Let me find the plus or minus symbol. Let me type these out. Now, I plotted on the y-axis distance to the x-axis time, so really this thing has units of meters per second. I should put that in. Second. And then the y-intercept is just distance, so let me put that y-intercept units in. And I want to change the font so everybody can see this thing. Let me make the font bigger. I'll make it real big. I'll hit apply and save. Okay, that's a little bit too big, but that way everybody can see it. So you all see that, right? Now what did I do wrong there? What's wrong with what I typed? Anybody? You don't see anything wrong? Based on what you learned in 205 about doing curve fits and reporting values to the correct number of significant figures? Didn't I report the slope incorrectly? Yeah, too many sig figs. In fact, I should report the slope as 0.03, right? Because the slope, the uncertainty of the slope is 0.03. It's telling me the duffel digit. So let me go back. The uncertainty tells me the duffel digit in the slope. And then the uncertainty in the y-intercept is really 0.2. So really I should write this as the following way. Now that's the correct way to write it. So you want to write this correctly. By the way, if I double click on here, I can get rid of the rectangular frame. And you don't have to make the font that huge. By the way, when you copy and paste your graphs into the lab report, I need to be able to see everything. I'm older than you folks. Okay, so I don't want to have to take out a magnifying glass to read stuff, okay? So you want to make sure I can read it. So then I would take this graph. Now I have everything I need for the graph. Let me move this out of the way. Okay, so now I can take this and copy and paste it in the graph. If you want to get rid of it, you can. If you want to get rid of that box, you can. So I deleted it. And then I can move this around. So then I would take this graph, go edit, copy, and then I would go into my Word document and paste my graph. Well, actually, normally you paste it below the data table. There it is. Okay. Okay, I have two of them from last time. Now, so there's my graph of the data from the previous table. Notice that it wants you to put a title for the data table. What I do differently from other instructors is that I want you to put a figure caption for every graph. Typically what happens when students do a lab report, they create the graph and maybe they extract some information from it, and then when they're asked to write a conclusion, they don't say a darn thing about the graph. I mean, the graph is one of the most important parts of the experiment because it organizes your data and allows you to see systematic trends. A lot of times students see it as just something that the instructor told them to do. You need to say something about the graph. So in every graph, you should put a figure caption. Now, if the graph involves a curve fit, then you should say what you graphed. You should describe, you can tell them, you got to say what the curve fitting parameters are. And then you should say something about whether or not your data agrees with the curve fit, because your curve fit is based on the theory. I don't expect more than 3 sentences, but you got to say something intelligent about the graph. So every graph requires a figure caption. So this lab requires you to make 3 graphs. So along with each graph, you have to have a figure caption for each one. Okay? Because you're going to have one for this, one for the light bulb, and then one for the last part. So I always have a figure caption. So this is what I expect from a graph. I need to see everything labeled. I need to see the results of your curve fit, and I need to see a figure caption. Those are my expectations. Generally, when I grade a lab, I actually have a lab report I'll send you, but you can say, this is, let me do this, figure 1. This is a graph of position, it says time. The results of the curve fit, I'll just say the results of the curve fit are, and then you can say what the curve fitting parameters mean, and then say something about whether the curve fit agrees with the theory or with the data. That's it. Okay, that's all you really need to say. I'm just trying to get you to think about what you're looking at. And really, what I'm looking at is if you're doing that. Okay, unless you say something really bizarre, I won't take, if it's not 100% correct, I'm not going to take off points. I just want you to do it. I wanted to see that you're thinking about the graph. And if this was a junior level course, then I would be more strict as to my expectations from that figure caption. Okay, so basically I only take off points if there's nothing there, or if it's part, you know, if it just says, because some students will just do this and leave it at that. Like, what the heck, what kind of a figure caption is that? Okay, say some more. Okay, so basically I will only take points if you don't say enough, if you don't say stuff, or if it's incomplete, or if you say something really bizarre. Okay? And on this graph, if you don't show me the curve fit results on the graph or below it, somewhere, then I take off points. I need to see that, because I need to see that you know what you're doing. Okay? I need to see that you know what you're doing. This lab report is evidence to me that you know what you're doing. And it also shows me what you don't know, what you don't know. Okay? Okay. So is everyone clear on the software and the graphing? And you can see this is not too bad, this software. Now, you will be creating some graphs. Hold on a second, let me find the graph again. You will be creating some graphs for which there is no function. So if you go to Fit Wizard, you can create a user-defined function. I have one already listed. You can create a user-defined function for you to do a curve fit. And in this lab, you're going to do this. So here I put the parameters A and B. I can say A star X plus B. And then I can say, call this user equation number 4. And then hit save. And then this function will be there. And then when I want to do a curve fit, I check the button, fit with selected user function. And then I can do the curve fit with that function. Now be careful, because this is a new program beta version. If you type the equation incorrectly and you do the curve fit, the program will lock up, completely lock up. So whatever equation you type, make sure it's typed somewhere else so you can copy and paste it, especially if it's a complicated equation. Okay? It will lock up if you type this equation wrong and you do a curve fit. Now, it does have built-in functions. It has exponential growth, exponential decay, polynomial functions, all kind of stuff. There's some basic functions. Some of them to me are not so basics, but they call them basic. Okay, and then there's, I never use the plugin functions. So there's all kind of stuff in here. There's more functions built into this one than in graphical analysis. Okay. So for parts 2 and 3, I'm sorry, for parts 3 and 4 of the lab, you might need to use some of the built-in functions to do a curve fit if you're using Davis. Okay. So you have all kind of complicated curve fit functions. And this is going to be important at the end of the semester, because at the end of the semester you're going to be building a very complicated equation, which is really based on, I don't know if you can see it there, there's one called Lorenz in here. You basically have to modify this one. Okay, so this has every, I mean, you can think of a function that probably has a complicated version of it, or you can create it. Okay, so if you create one, you have to use the Fit Wizard. Otherwise, if you don't, you're free to use graphical analysis or this one or anything that's free, as long as I'm able to get the curve fitting parameters and uncertainty from the software. If you are using a piece of software that's neither graphical analysis or Davis, then let me know, because I'd like to know what's available. There's another one called NuPlot That's free also. Okay, I need to talk about the lab now, all right? So let me go to the board and switch views before I forget. Okay, so the first part of the lab, you're going to be testing Ohm's law. These labs seem trivial after you're done with them, after you've had, like, especially after you've had circuits, but the first time you do this stuff, it's not trivial because you're learning how to wire and things like that. So if you struggle, be patient, you'll get this stuff down. So you're going to have your power supply that you can vary. Remember, you only have 6 settings. You can take a wire from the positive side to the power supply and connect to the resistor. This is a 1,000 ohm resistor. You take the other side of the resistor and connect it to the positive side of the ammeter. Then you take another wire that goes from the common of the ammeter and connect it to the negative side of the battery. And what's important is that you really should have this not connected until you're ready to make measurements. And you should actually disconnect it, switch to the correct setting on the meter, and then make your final connection. Because, you know, like I said, if you're flipping switches while this is in the circuit, you might blow a fuse. Now, the current's going to be sufficiently low in this lab. Number one, you don't have to worry about getting electrocuted. And number two, it's going to be hard to blow a fuse. But of course, I've had experiences where people have figured out how to blow fuses, even in the case where the current's low. Okay. So you're going to have your ammeter, and you want to use the good one. You want to use the big one to make the measurements. Don't use the other one. In fact, the other meter only has a 10 amp scale. So you're hardly going to, you would probably read 0 all the time. Okay, so you want to use this. And I should caution you, because I was reading through the manual, on both of these meters, the 10 amp scale has no fuse on it. So if you apply more than 10 amps to this thing for more than, it says 10 seconds, you'll probably melt everything in here. Okay, so don't, well, just be careful. Okay, just be careful. You don't want more than 10 amps going through here. My guess is you probably wouldn't have a situation of that. So yeah, the resistor is one kilo ohm. Yeah, 10 amps is a lot of amps, but you know, your air conditioner, your microwave, your refrigerator, when those things are kicked on, when in the process of kicking on, they're drawing a lot of current. Okay, so this is a 1 kilo ohm resistor. How do you know, you have a bunch of resistors, how do you know the resistor is 1 kilo ohm? Well, there's a color code on it. And in fact, the resistor, the 1 kilo ohm resistor, looks like this. I'm going to draw a blown up picture of the resistor. And I'm going to tell you the most common, resistor code. Okay. So the 1 kilo ohm resistor will be, I don't have brown. Let me see if I, well, I'll just tell you the colors because I don't have a brown color. It'll be brown, black, red. And then, so there'll be 3 bands. I'm going to do a different one. first three tell you something about the resistor, and there's a fourth band which tells you how good the resistor is. Okay. Yes, Patrick. So the fourth band tells you it's either going to be silver or gold. Gold is like 1% and silver is 5%. In other words, it tells you if this represents, this one actually represents 2,000 ohms. If the next band is gold, it's 2,000 plus or minus 1%. So let me tell you something about the color code. The color code goes this way. It goes brown, black, red, orange, yellow, green, blue, and now let's forget the last two. It's either gray and white or white and gray, I forget. Okay. But the digits, oh, these are backwards. Sorry. So let me write the digits. 0, 1, 2, 3, 4, 5, 6, 7, and 8 and 9. White and gray or gray and white. I forget those two. Gray is 8 and white's 9. Okay. Yeah, I don't. For some reason, I don't remember those two. Now, you have a card. You also have a card that's about. I don't have it. It's about this size. That came with your kit, and it gives you the color code for the resistor. Okay. The card gives you the color code, so you should learn how to read that card. So in this particular example, so if I want to determine what the resistance of this guy is, the first band tells you the first digit in the resistor, so it's 2. The second one gives you the second digit, which is 0. And the third one tells you the exponent, which is 2. 20 times 10 to the second is 2,000 ohms. So in your case, the 1,000 ohm resistor will be brown, black, red. Okay? So you want to get familiarized with using the color code, especially if you want to be an electrical engineer. Okay? You should know that color code. And there is actually another color code with 4 bands. That one I don't remember. I actually have to look at the card. And the reason why I don't remember is because I learned this one. Okay? Okay, so you use your 1,000 ohm resistor. You're measuring the current. But you also got to measure the voltage. And you're going to plot voltage as a function of current. You're going to get a graph. You're going to fit to y equals mx plus b. What's the slope going to tell you? If I make this graph, what's the slope going to tell you? What does it physically represent? Yeah, it represents resistance. Hold on a second. Okay. So the slope is going to be resistance. And notice I'm always doing a fit with a y-intercept because I don't want to force the data through the origin. It could be that I have some sort of systematic error in my experiment. So I always want to include a y-intercept, and this will take into account any systematic error I might have in my experiment. Never force this to be 0. So let me ask you a question. I determine the slope. And I ask this all the time, even in Physics A. Those of you at Physics A with me know I ask this question all the time. So let's say the slope gives me a value of 995 plus or minus 3 ohms. And the color code is 1000 ohms. Does my measurement agree with that color code value? So, Patrick, why do you say yes? Ah, good, good. It depends. I'm glad. Okay, good. It depends on what the color band is. So let's say the color band's gold, 1%. So really, I lied to you, right? I shouldn't write it this way because every measurement doesn't just represent a number. Is it 5%? I'm sorry, gold is 5%. Every measurement represents a number. I'm sorry. Every measurement does not represent a number. It represents a range of values. Well, 5%, that's 50 ohms, right? So they agree. What do I mean by they agree? The range of values that's quoted by the color code overlaps the range of values from my measurement. Remember, anytime you make a measurement, you're not getting a number, you're getting a range of values. And so my range of values that I measured overlaps with the quoted resistance value. Okay. Of course, if I had, then these wouldn't agree, right? Of course, you're going to compare this to what you measure with the meter too. Right? You'll compare this to what and you're going to get good results. This lab, you always get good results. Okay. So I'm going to ask, a lot of times in a lab, I'm going to ask, do the results agree with, the two results agree with each other? And what you got to do is look at whether the values overlap with each other. And if they don't, what does that mean if they don't? What kind of error are we dealing with if the two values don't agree? Are we dealing with a random error or systematic error? And I should say this way. What kind of error does it indicate if these two values don't agree with each other? Yeah, it indicates systematic error. It's indicative of. I don't want to say it is, but it's indicative of. Because I might not have taken into account everything. So it's indicative of the fact that I have a systematic error, maybe, you know, and that can be, you know, it's going to be determined by maybe what my intercept is or something. Okay. And the reason why I say that is because this number that I obtained here is representative of my random errors. I think, but this one is actually indicative of random and systematic because an engineer quoted this, okay? But this is indicative of just random errors only. Because in Physics 210, and even in the 200 series, we don't try to figure out what the actual systematic errors are. We don't estimate them. We only estimate the random errors. Is that clear? Okay. Now, in part 3, is the circuit's similar. The only thing you're going to use is a bulb. You're going to use a landscaping light. So let me replace this with a landscaping light. And so this is a device that does not obey Ohm's law. And thus you'll get a graph that probably looks like this. you're only going to have 6 data points, okay? You're only going to have 6 data points. It's going to be actually hard to see the curve. And what do I want you to do in this case? When you make the graph, I want you to find the equation that best fits your data. That's what I want. Okay, so to be honest with you, I can fit that to a 94th degree polynomial, no problem. But don't do that. Okay? You don't need that many parameters. So in fact, don't use more than 3 fitting parameters. Find a function that will fit this data well, but don't use more than 3 fitting parameters, okay? And then there's a little conclusion at the end of the lab. I don't want you to write a formal conclusion. Basically, in this lab, I just want you to tell me what you learned, what function works best, and give me an interpretation. I'm grading you based on whether or not you did the interpretation and you didn't say anything silly. I mean, really silly. Okay. If your interpretation is not correct, that's fine. I just want you to think. Okay? I just want you to think. Are we okay with that? Okay. So I do want to say something about, and I forgot to say this before, about the voltmeter and the ammeter before I talk about the last part of the lab. The ammeter and the voltmeter have to have special characteristics. Number one, when you measure voltage, obviously it has to be, the voltage across the meter has to be the same as the voltage across the resistor or the light bulb. It's like when you take a thermometer and you try to measure the temperature of a container full of water. When the mercury stops going up, its temperature is at the same value as the temperature of the water. And you don't want the thermometer to actually affect the temperature of the system, or you want to minimize the effect. No, you do have a potentiometer. Okay, I'll talk about part 4 in a bit. Okay, so you want the thermometer to not affect the temperature, so that's why it's small, right? It has it's small thermal inertia, so it doesn't affect the temperature of the system. Well, when you measure voltage across a resistor, you do not want the voltmeter to affect the voltage across the bulb or the resistor. What does that mean? You don't want the resistor to draw any current. You don't want this. You don't want the voltmeter to bring up some current, take away the current from the bulb. Because if you take away current from the bulb, then its resistance will be less than really what it is. And so the voltmeter has a very high resistance. Okay, we're talking, especially with the new ones, these are like 10 to the 8th ohms and higher. The real old ones, the dial ones, some of them are like 1,000 ohms. And usually when the class is on ground, I give you one that's 1,000 ohms, just so you can see the effect. You're right, in theory you want it to be infinite, but in reality they're high. We just say they're high. Okay. Now, what about the ammeter? Obviously, when you use the ammeter, you want the same amount of current going through the ammeter as you do through the bulb or the resistor. But you don't want the ammeter to affect the amount of current going through your circuit. So you want the ammeter resistance to be really low. That's right. You want it to be a very low resistance. And so depending on how you're measuring current, what your current range is, actually, in order for you to measure current, you actually need a resistor. And so the resistor value changes depending on the scale you're using. So in a 10 amp scale, the resistance is really low. And you can actually measure the resistance of this thing by taking this meter and connecting it to the other meter. Use the other meter to measure resistance, and then just plugging in the meter like, hold on a second. Plugging in the meter like this, and then to the other one use the other one to measure the resistance. And you can see on the 10 amp scale, the resistance is really low. And then when you go to the 200 milliamp scale, the resistance you can tell is higher. Okay. Now here's the thing too. You can make, on this thing, you can make measurements for this lab on the 200 milliamp scale and on the 20 milliamp scale. On the 20 milliamp scale, you have a higher resistance. And you should play with this and check the difference. Okay, so in a 20 milliamp scale, the resistor is higher, which means that it's going to make, for part 2, it's going to make your slope higher because of its resistance. On the 200 milliamp scale, it has a lower resistance, which means you're going to have a more accurate reading for the resistance. However, you're going to have less sig figs. So you have to decide what's going to work better for you. Okay? So the higher you go on the scale, the less sig figs you have. Does that make sense? Now, if you use a 10 amp scale, you won't be able to read anything probably. At least not with this one. The other one that I had will. Okay? And if you use a cheap one, it'll never read anything. Okay? Because the current's going to be very low in this thing. Most multimeters, in fact, the one that I was going to have you buy, has a microamp scale. This one does not. Okay, most of them have a microamp scale. This one does not. Okay. So I want to make sure you understand that these have to have special properties in order for you to make a measurement. Now, so let me talk about the last part. I have a few minutes. And I will use next week to talk about the last part too. The last part's harder because you're going to look at a diode. You're going to look at the current through a diode. A diode is a non-ohmic material. And the equation that describes the current as a function of voltage is much more complicated. But you can easily do a curve fit. Okay? So your circuit is going to look like this. I'm trying to find one of my markers. Hold on a second. Okay. So the circuit is going to look like this. You're going to have 12 volts supply. This is going to be fixed. Okay? So you're going to actually, in this particular one, you're going to have a fixed voltage. Here at least. Then you're going to have a 560 ohm resistor. The purpose of this is to limit current. And this is going to be is a 1 kilo ohm, 1000 ohm potentiometer. So basically, it has three connections on it, 3 terminals. And let me show, maybe I'll show you the drawing, the circuit drawing in the lab. And then I'll show you the diode. Oh, here it is. That's what the circuit looks like. So the question is, what is a potentiometer? What does it do? It's a way to be, it gives you a way to vary voltage. It gives you a way to vary voltage. So there's three connections on them. There's the connection between the ends, and then this thing called a sweep. If you make an electrical connection between these two ends, you get the full 1,000 ohms. If you make the connection between any two adjacent terminals, you'll be able to vary the resistance. And so what you're going to do is you're going to use the middle terminal. This is the middle terminal on the dial. It has a dial on it. It's a little device on a board that has a dial on it. Tyler actually went through the trouble to actually mount this on a board. And so this is the middle terminal. And you're going to connect it to an ammeter. The other side of the ammeter goes to a diode. And I'll say what a diode does just briefly. And this goes to the negative side. So that's negative, that's the negative side, that's the negative side. Okay? And then we use a voltmeter to measure voltage. So this is going to be the harder one for you to wire. This is the one that worries me a little bit more and I worry in terms of blowing fuses. You're not going to be drawing a huge amount of current, but I just worry about blowing fuses. Okay. And Tyler has office hours on Thursday on Zoom, so he can help you. So what does this thing do? This thing only lets current go in one direction. So a diode lets current, I should say charge. I don't want to say current because current is redundant. Let's charge flow in one direction. So your diode is going to look like this. And I forget which one he put in the kit because mine's different. But there'll be a band here. And so the current's going to want to go this way in the direction of the, okay? The current's going to want to go this way. There'll be a band here. Usually they're black. Mine is, the one I have here is not. Okay? And this thing will not conduct until the voltage drop is a certain value. So there's a dial on here. You're going to vary the dial, and that's going to vary the voltage across this guy. At some point, it'll start turning on, and the current will increase. In fact, the current will look like this. This one, the graph is going to be backwards. We're going to plot I versus delta V. The graph will look like this. In order for you to graph this very accurately, you need to actually measure a lot of data points. And I highly recommend you're going to collect about 25, 26 data points. Where do you collect most of the data points? Where it curves. You will find when this thing just barely turns on, a small tap on the dial will make a huge difference in the current. And that's where you want to collect all your data. This is an exponential growth. This is how the current depends on the voltage. It's exponential. Well, I'm going to talk about this more next week. But the key here in this lab is you have to, before you take data, you have to play around with it and see when it turns on. You got to get a feeling for when you turn the dial, how much V changes and how much A changes. Because just a little tap of the potentiometer will make big changes here, at least at this one. Okay? So when you start seeing current, you have to make small little teeny adjustments on the dial. That changes where this is going. Okay? By changing the dial on the potentiometer, that changes where this slider is on the potentiometer. So if the slider is over here, resistance is 0. If the slider is all at the end, the resistance is the full 1,000 ohms. So this will be the tough part of the lab because number one, it's hard to wire. Number two, you want to learn how to collect data properly so you can fit the data here. So this lab really is more on technique than anything. Okay. Do you have any questions? So I will continue this discussion next week. I'll talk a little bit more about this. So yeah, go ahead and finish your multimeter quiz and then start in the Ohm's law. And I give you, normally this is when we do this class on ground, this is actually a 1-week lab. Because everything's set up right away in the lab, you can just go in and take the data real quick. But this is, when it's done online, everything's different. So you do have more time to do these experiments. All right, so I'm going to stop here because I have another class in 7 minutes. So if I don't see you, have a good weekend.